Working beyond ambient wet bulb constraints. Exhaust air evaporative cooling addresses both these limitations by relocating the evaporative process from the supply airstream to the extract airstream. In a typical configuration, return air from the conditioned space is passed through an adiabatic humidifier, where it is cooled through evaporation and approaches saturation. This cooled exhaust air is then used as a heat sink within an air-to-air heat exchanger or runaround coil, transferring heat from the incoming fresh air without any direct mixing of the two airstreams. The extracted air, now both cooler and more humid, is discharged to the atmosphere, while the supply air is sensibly cooled before entering the occupied space. Because the evaporation process is confined to the exhaust side, no additional moisture is introduced into the building, allowing the system to operate at maximum evaporative capacity without compromising internal conditions. This seemingly modest rearrangement has significant thermodynamic implications. By introducing evaporative cooling on the exhaust side, the extract air temperature can be significantly reduced, increasing the temperature differential across the heat exchanger. This enhances the driving force for heat transfer and allows the heat recovery device to operate as a cooling component during warm conditions. In practical terms, supply air temperature can reduce by 10 degrees Kelvin or more under favourable conditions, using primarily the energy required to move air and circulate water, although this must be balanced against increased air side pressure drop and associated fan power. A further advantage arises from the choice of working fluid. Whereas conventional indirect evaporative cooling systems rely on ambient air as the secondary airstream, EAEC systems use an indoor air extract air. In many mechanically conditioned buildings, this air is maintained with a relatively controlled range of temperature and humidity, although actual conditions will vary significantly with occupancy, internal gains, and application. The use of extract air moderates the influence of ambient humidity, providing more stable performance than systems relying directly on outdoor air. However, the process remains fundamentally bound by wet bulb conditions, and effectiveness still varies with operating conditions. In thermodynamic terms, the limiting wet bulb temperature becomes that of the extract air rather than the ambient air, partially mitigating one of the principal constraints on evaporative cooling.